All right, welcome. Hello, everyone. And thanks for joining. My name is Mark Mala, and I lead engineering at NetActuate. I've been building and operating global networks and Anycast platforms at scale for a long time. One of my favorite things to say is that everyone uses some kind of network, load balancing, database, application servers, or storage, and no one uses those things in the same way. One of the best parts of my job is being able to tackle many different types of challenges for business or technical reasons every day. This session is a field guide to Anycast deployment. We're not going to try to turn this into a deep BGP protocol class. Instead, I want to give you a practical overview of what works, where people get into trouble, and how to think about Anycast as a complete service, not just a routing trick. The plan is to spend roughly 35 to 40 minutes on content and leave some time for questions at the end so that we can get everyone out of here before the top of the hour. Here's what I plan to cover today. We'll start with why Anycast matters at all. That will be the high-level value story for both technical and business folks. Then we'll talk about owning your identity on the internet. That means IP addresses, ASNs, and the paperwork that keeps your routes trusted. From there, we will move into architecture and application design. This is where we look at how to attach real services to an Anycast edge without breaking sessions or state. Next, we'll look at routing policy, traffic engineering, and how to work with multiple providers. And finally, we'll wrap up the main content with observability, DDoS strategy, and the human side of operations, and a checklist you can take back to your teams. Before we jump in, a quick word on who we are and why we care so much about this problem. NetActuate operates a large global footprint with more than 50 data center locations and a long history of running Anycast-based services. We are the fourth largest network in the world by number of peers or other networks that we connect to. We power over 60% of the world's TLDs, operate hundreds of unique Anycast networks, including a root server, or just DOT in DNS terms, and much more. We are vendor and cloud neutral. That means we help customers integrate on-premise infrastructure, multiple clouds, and third-party services, often with Anycast in front. Our typical customers are deploying a global SaaS application or footprint to many geographic regions, and they want to partner with the expertise to manage the infrastructure and the network so that they can focus on innovating higher up the stack. The lessons I'll go over today come from being in the trenches, operating these environments every day for over the past 2 decades. To start, let's ground the idea of Anycast in one mental picture. Imagine a single IP address, like a front door, but that door exists in many physical locations around the world. Each of those locations announces the same IP prefix into BGP. Routers across the internet pick what they believe is the closest or best path to that prefix. From a user perspective, there's just one address to connect to. The network makes the decision about which location actually serves the request. That simple idea is the foundation of global DNS, CDNs, and many modern security and access services. In the event of a network failure, Anycast automatically routes the user to the next closest location without requiring load balancers or other logic. This isn't just a theoretical idea. Some of the most widely used internet services depend on Anycast. Global DNS services, including the root server system, TLDs, and public resolvers, rely on Anycast to put DNS capacity close to users. CDNs and security edges Anycast their front doors, then move traffic over private backbones or optimized partner networks. And cloud providers expose similar patterns to products like global accelerators or HTTP load balancers. In all of these cases, you see the same theme: layer 3 Anycast at the edge, service offload, policies, and smarter routing once traffic is inside of that provider. Gotta finish my espresso. Global DNS is powered by Anycast, and you use it every day without knowing. This is everything from the root servers to the infrastructure powering TLDs and the domain registrars and registries that power every service you access. Finally, most recursive DNS services also use Anycast, enabling your computer, your phone, any device in your network to resolve those domains. Google Public DNS and Cloudflare Public Resolvers you've probably used or programmed yourself. And from the outside, you just see 8.8.8.8 or 1.1.1.1 when you program those in as your DNS servers. Literally billions of devices use those addresses. So under the hood, those IPs are anycasted from many locations. Your queries usually land at a resolver close to you, but the capacity and the policies behind them are handled by a much larger distributed system that sit behind that edge. The key takeaway is that Anycast gives them global reach and low latency without asking the end user to know anything about their internal layout. Every major global CDN is also powered by Anycast, typically both at the DNS and the edge services level. They use Anycast as their default way to accept traffic. A user connects to a single hostname or address. BGP steers that connection to a nearby edge data center that participates in Anycast. From there, the CDN services traffic from each POP's local edge, providing fast and performant access to cache content. In many cases, they also move traffic over a private backbone, apply security policies, and help connect to origin paths wherever it's most efficient. If you are thinking about building your own edge, you can borrow this pattern even if your footprint is much smaller. And finally, cloud load balancers that offer global Anycasted front ends also follow a similar pattern. They give you one or a small set of VIPs that are Anycasted globally. Users connect to that address, and the cloud provider uses health checks, geography, and latency to steer requests to backends. This can span multiple regions, can be multi-cloud, or even connect to on-premise backends over VPN or direct connect cloud on-ramp style services. For many organizations, besides day-to-day use of DNS, that's really the first time that they experience Anycast. Building and Anycasting your own global traffic load balancer is a very common pattern today to increase performance, reduce costs, but ultimately, if you've been following along with recent AWS and Cloudflare outages, there's something that can give you full control over where you steer your traffic. If any of these fundamental use cases make sense to you, know that with the right planning, you too can take advantage of Anycast in the same way that these large global platforms do. And in many cases, your competitors already probably are. So let's get into what you need to build Anycast. And before the network, it starts with IP space. So we'll go into a little bit of history. At the very top of the global IP addressing system really sits the Internet Assigned Numbers Authority, or IANA. IANA is responsible for coordinating the global pool of IP addresses and autonomous system numbers, making sure that they are unique and consistent worldwide. IANA used to allocate large blocks of number resources to the regional internet registries, which then distribute those resources to providers, enterprises, and other organizations. IP addresses and ASNs come from these regional internet registries that manage number resources for the global internet. Each region has a registry, such as ARIN for North America, RIPE NCC for much of Europe and parts of the Middle East, APNIC for Asia and the Pacific, and so on. These organizations allocate and track number resources and maintain important databases. There are also some more specific or national registries under APNIC, specifically such as CNIC, JPNIC, IRINN, and others. The central IANA pool of IPv4 addresses was officially exhausted in 2011, when the last remaining blocks were allocated to the regional internet registries. And the last regional registry to make a final allocation from its remaining IPv4 pool was LACNIC, which handed out the last block of IPv4 space over 5 years ago. And that was on August 21st, 2020. That means for the most part, you'll need to buy IPv4 space in order to do Anycast. At one point, it was almost as expensive as Bitcoin. Even if you acquire space on a secondary market or through leasing it, it's valuable to understand which RIRs govern your prefixes, how those RIRs relate back to IANA, and to maintain clean, accurate records with them. This ensures your Anycast prefixes are properly registered, globally routable, and easier to troubleshoot when something goes wrong. Because IPv4 space is exhausted, most new IPv4 deployments rely on existing space that has changed hands. That might be address space you purchase through a transfer, space you acquire with a company, or prefixes you lease from a broker or a marketplace. Leasing is now quite common, but it introduces extra dependencies, and you should be wary. You need to understand who controls the parent objects, how long-term the lease is, and what happens if the business relationship changes. For IPv6, you can usually obtain space directly from an RIR and design with much more flexibility. Two common platforms you can lease and purchase IPv4 space from that are known and trusted are IPv4.global, run by Hilco, and IPXO. It's worth noting that Anycasting requires a minimum of an IPv4/24 or Class C of address space and a /48 of IPv6 to enter the global routing table. That's true even if you plan to use only one IP address. You should also often consider more space to announce secondary and tertiary services, or to give yourself the flexibility to announce more specifics, topics that we'll cover in a more technical webinar. I recommend that ultimately, just like Anycasting gives you significant choice, for true provider independence, you should own your own IP space in your ASN, at least for your customer-facing services. When you plan Anycast, I like to think of prefixes as policy containers. So you rarely want one giant block that carries all traffic for every product and every customer. Instead, carve out prefixes that line up with service tiers, risk profiles, or geographic needs. For example, you might have one prefix for free user-facing DNS, another for enterprise customers, and another for internal or control plane traffic. You should also use separate prefixes for secondary and tertiary services, and a real-world best practice is to announce those prefixes from different networks. That can be with the same provider or different providers. You also want to plan your IPv4 and IPv6 blocks together so that you can keep policy in sync across both address families. That avoids ugly surprises later when you expand your IPv6 usage. Routing, security, and clarity are especially important for Anycast. IRR objects document which AS is expected to originate which prefixes, and which AS sets and route sets describe your relationships. RPKI adds cryptographic validation through route origin authorizations, or ROAs, which allow networks to route announcements that do not match the expected origin. For an Anycast service, you want automation that ensures every prefix you deploy has accurate IRR entries and valid up-to-date ROAs. That reduces the risk of hijacks and accidental leaks, and it improves your standing with peers and upstreams. Some places to start: if you're with Aaron, they have a free service, Aaron IRR in North America, or use RADB as a semi-commercial option. I think it's about $500 a year. If you already have a running platform, moving to Anycast should be done in stages, not as a single event. A safe pattern is to Anycast your front doors first. That might be DNS, an API gateway, or a routing control plane, while keeping backend services where they are. Any kind of cacheable content is an easy win. Once that's stable, you can progressively move more components into the edge sites, always with clear rollback options. Stateful or highly coupled services deserve special care. You may need new approaches for session affinity, caching, or data replication before you Anycast those entry points. If you're starting out and you're building a new platform, you have more freedom to design for Anycast from day one. Begin with services that are stateless or easy to replicate: DNS, simple APIs, or authentication redirects. They're forgiving, and they can help you test your routing and operational model. Next, think hard about how your application state is stored and accessed. Aim for patterns where a user can land in a different location over time without breaking their experience. Treat your points of presence as repeatable units built from automation. That makes it easier to scale and to scale out and to recover from failures. Consider data sovereignty, business, and technical objectives that can influence your overall architecture. At a high level, most successful Anycast architectures share a similar shape. At the edge, you announce Anycast prefixes into multiple providers and exchanges. That gives you layer 3 ingress near users. Next, it's common to see deployments where every POP is considered a silo. That's often in deployments where specific assets, gateways, stateless services, etc., are able to be managed from central locations to improve performance. In the second case, many operators run a private backbone or an overlay network so they can control how traffic moves between regions. This can take various shapes depending on your deployment. Near the applications, Layer 7 components handle HTTP routing, gRPC, or other protocol-specific logic. That's where you apply policy that is hard to express in BGP alone. If you have an existing stack, your applications will feel Anycast, especially if they rely on connection-oriented protocols or sticky sessions. First, identify the parts of your system that truly require a user stay within the same backend instance for a period of time. Commonly, that's things like payment flows, shopping carts, or maybe specific administrative tasks. You'll want to design your state management so that if a user lands on a different POP, they can still be served correctly. And that could involve centralized storage, caching layers, or specific replication strategies. Another best practice is to include POP and region identifiers in headers and logs. It makes it much easier to trace issues through your distributed system. You can use many modern operating systems and as well as open source tooling to do this. You really want to aim for being able to stand up new locations with a single command, as well as easily scale across providers and platforms horizontally. We have some existing webinars and presentations on using some of these platforms and automating deployments, and we'll have more in the future that you can review. So we're not going to cover them in great detail here. In POP load balancing. I would say that Anycast does not remove the need for load balancing inside each POP. From the outside, BGP will steer users to a POP. Inside the POP, you still need to distribute traffic across multiple hosts or services. You can use Layer 3 or Layer 4 mechanisms such as ECMP or network load balancers, and Layer 7 load balancers on top when you need HTTP or protocol-specific routing. One of my favorite things is that you can also double Anycast by Anycasting resources in a POP in combination with ECMP, and allow yourself the flexibility for inter-POP load shedding to other regions over transport or tunnels with different network weights. That's a more advanced topic that we're excited to cover in a future presentation as well. Always aim for active-active designs inside the POP with automation that can remove and add nodes based on health, and always build out in-POP redundancy to upstream edges to allow for maintenance events. IPv6 is no longer an afterthought for global services. I know some people seem to still wish that it was, but as you can see on the right, IPv6 traffic to google.com has increased to almost 50% in 2025. So when you design Anycast, plan for IPv6 alongside IPv4. Allocate /48 blocks per service tier or region so that your policy model matches across both address families. An easy way that we like to think about this is simply mirror a /48 of IPv6 with every class C or /24 that you're Anycasting. Another thing to be aware of is that at the transport layer, newer protocols such as QUIC and HTTP3, which can run over UDP, they have a different behavior under loss or path changes than standard TCP protocols. So you're going to want to test your Anycast design with a mix of different transports, the ones that your applications actually use, and not just with simple pings. Don't just look at things from the network level. Ultimately, if IPv6 isn't something you can build out deep into your stack, at the very least, terminate it at your edges so that you're dual stacked to the outside world. Your success with Anycast depends heavily on when and how you announce or withdraw routes. BGP announcements should be driven by health checks that reflect real user experience, not just the basic reachability of a host. When something is wrong, it's better to fail closed and withdraw a prefix from a POP than to keep accepting traffic that your application cannot handle correctly. You're going to want to use features such as graceful shutdown and BFD to lower packet loss during maintenance or failures and to shrink convergence times. Ensure that you don't flap routes by having the correct gates and logic in places. Too much automation can cause your prefix to be dampened and extend an outage unintentionally. So as with anything, there's a balance. We actually had a customer that planned maintenance events and automated stopping and starting BGP sessions. And due to a rollout, they were stopping and starting sessions, I think, multiple times a minute across, hundreds of servers. And it effectively caused an outage for themselves. So it's definitely something that you want to consider in your design. Capacity planning for Anycast is about more than just total requests per second. You want to know what happens when you lose a site or even a whole region during peak traffic. So that usually means designing your platform for N-1 or N-2 failures. It's pretty common in many deployments to have super POPs that have more capacity and better connectivity than more specific subset regions. Those locations need to be able to absorb the extra load when those smaller sites fail. And if you don't follow that model, you want to understand how load will distribute to the remaining POPs that you're anycasting from. I recommend running regular exercises where you simulate or actually withdraw prefixes from regions or providers and watch what happens. That will reveal hidden constraints before real incidents do. And one of the benefits, obviously, of running Anycast is that you can take a pop offline or region offline at slightly higher latency for an hour or days or maybe a week if you need to. Most Anycast deployments rely on more than one upstream or peer. Multiple providers give you reach, they give you diversity, and they give you better cost options, but they can also create policy complexity. If your policies are inconsistent, you can unintentionally create black holes or odd routing paths. BGP communities are the primary tool for turning your intentions into routing decisions. You can label routes so that providers keep traffic in region, avoid specific peers, or prefer cheaper paths when there is a choice. Spend time understanding each of your provider's community support and build a clear, documented policy model around it. Considering a multi-provider strategy makes a lot of sense in the context of building multiple redundant networks. For example, for your primary DNS, secondary, and tertiary, build 3 different Anycast networks, with each network across the same provider instead of mixing them. This gives you not just provider, but vendor and upstream and even POP diversity. Here at NetActuate, we actually operate over 5 distinct Anycast backbones, each with a similar geographic footprint that uses different data centers, different vendors, different upstreams, and even different hardware. It's a unique approach that allows you to deploy redundancy across our entire stack. We also partner with other providers, and we can help you operate third-party networks because of our diversity-first approach and how we partner with you. Observability is where you turn Anycast from a black box into something you can manage deliberately. First, you want to measure latency and reachability from many locations that approximate your users. A single monitoring point is always going to be blind to local issues. Second, track how paths and routes change over time for your important prefixes. That helps you understand the impact of provider changes and your own policy adjustments. Third, define and track service level objectives per region and per tier. That lets you see whether Anycast is actually delivering the latency and availability improvements you expect. Fourth, don't just consider latency and packet loss, but throughput. Depending on your use case, being able to push more data at a slightly higher latency is the difference between supporting a 4K stream and downscaling to HD or worse. And lastly, always look at passive data. Map the geosource of end users ingressing into your edge POPs and alert if you start to see unexpected traffic. For example, why are 30% of users from Sydney, Australia coming into my POP in Chicago? We've built that unique capability here that measures distance in kilometers from our edges back to end users. It's based on real-time flow data. That lets us easily score and assign a metric and see Anycast sinkholes and performance issues and take action, even if other alarms aren't being triggered yet. You need multiple vantage points to see the full picture. Synthetic probes from different cities and networks can continuously test things like DNS, HTTP, and TCP from the outside, catching localized regressions. But make sure you distribute those to expose a full mix of transit peering paths. It's not uncommon to have external probes very close to your edge report healthy while end users are suffering. Use flow data and logs inside of your own infrastructure to show you how traffic actually moves through your fabric and which prefixes or customers are active. And use external route collectors and looking glasses because they can reveal how the wider internet sees your announcements. That is especially useful when a provider change affects routing in ways your internal tools can't see. And lastly, from that passive data perspective, look at traffic watermarks. If you suddenly see an abnormal drop in traffic in a region, trigger a process to investigate, either in an automated or even a human way. I've listed some commercial and free and open source tools and platforms that are helpful starting points for monitoring all of these things that can help with them. And last but not least, using metadata. Collecting data is really only half the job. The value comes in how you use it. You're going to want to build signaling into your application stack so that you can enrich your data. Your goal is going to be to detect anomalies and regressions before customers open tickets. That means alerts tuned to user-facing impact, not just device metrics. Over time, you should tune routing policies and capacity plans based on real traffic patterns. Observability shows you which regions grow fastest and where performance is weak. After incidents, bring the data into structured reviews and let the findings drive policy and architecture changes so you don't repeat the same mistakes. If you already run an Anycast network and you're curious what we might see from our perspective, we're happy to provide a free performance assessment report based on some of our own internal tooling. Just reach out to me by email. And this could be an entire presentation on itself. If you operate Anycast services on the public internet, you should assume that DDoS traffic is part of normal life. So one important design technique here is to tier your prefixes. So services that face more risk, they can live on prefixes that you can steer to mitigation providers or isolate during large attacks. So that means, and this goes back to your prefix design, but it means that if you offer a freemium service, a shared service, an enterprise service, you should consider building networks with specific levels of mitigation to reduce blast radius. You never want a user on your free service to impact your most important enterprise customer. At the network layer, you should work with providers on filters to push them to the edge. Consider using things like FlowSpec where appropriate. And at the application layer, use rate limits, WAF rules, and other defenses aligned with your protocols. Here, we build out concentric circles of mitigation, considering the overall attack surface depending on your business and technical objectives. No customer is the same. The strongest designs use multiple layers of defense that can be activated in stages depending on the scale and the type of attack. As I said, this is a great topic with many details, and I think we'll probably have an hour-long deep dive just into Anycast and DDoS mitigation in the future. And finally, the hardest part about Anycast is often the human side. That can be your own team, it can be customers. But if you front critical services with Anycast, you need real 24/7 by 365 coverage, not best effort. Because the impact of a failure with Anycast can be global. You're going to want to invest in runbooks and game days so that your teams practice response before major incidents. That includes simulating regional failures and DDoS events. Also, don't get caught by needing to search for your carrier's contact information, your NOC, for IX or peers. Make sure that you have their contact information and you can get to the right people quickly. Treat routing policy as a sensitive control surface. So limit who can change it, use change reviews, and automate where possible so that you can roll back safely. A good strategy here that we like to implement is to extend more control to business-facing teams with appropriate gates that you set up yourself. So there are safe ways that you can enable controls that will allow business or less technical users, for example, your support organization, to stop announcements in the POP for maintenance or to reroute traffic without involving higher cost network engineers. And that can really pay dividends if it's something that you build into your stack from the start. Finally, always build data-enriched pipelines so that if you need to escalate, the issue is clear. One of the most common things we see in Anycast deployments are a lack of details surrounding an event or customer issue, making everything more complex, especially if you've got hundreds or thousands of servers and many POPs all around the world. Think beyond your NOC and network engineering and how you dashboard and really work to understand your stack globally. Over time, we see some myths repeat across many organizations. One is that Anycast is something that you deploy once and then forget. In reality, it adds a complex new layer of routing and operational complexity that needs ongoing attention. The internet is a living, breathing thing that changes every millisecond with fiber cuts, new peers, paths, and policies. Another that we see often is that Anycast can work well with commodity providers. While it's fine for learning and testing, running any major critical production service for pennies on the dollar, especially an Anycast platform, will eventually have repercussions. Have a serious conversation with yourself and your team to avoid being penny wise and pound foolish. At scale, Anycast is cost effective and will pay dividends if you do it right. Another common thing that we see is that more providers will increase reliability, but that can be a double-edged sword. Without consistent policy and good observability, each new provider that you add can add more places for things to go wrong. That's something that we see almost every single day. As the modern age of DevOps, stateless services, and immutable design patterns has taken over, it's also not uncommon to see legacy network teams with SOPs and MOPs looking to manually configure and deploy BGP. We really want to encourage you to avoid that thinking at all costs. In today's distributed world, you need to be able to quickly and autonomously stand up infrastructure for true scale. And finally, Anycast is not just a network and infrastructure play. Yes, it can be foundational. And yes, you can move many components off without involving the application teams in the beginning. But to truly take advantage of Anycast, you need to consider your entire architecture and build for global. So to close things out, here's a simple checklist you can use as a starting point. The first is preparation. Do you have a clean IP plan for both IPv4 and IPv6? A clear ASN strategy, accurate IRR and RPKI data for the prefixes that you care about. Map that to your business and technical requirements, be it for service tiers, data sovereignty, or performance. The second is building. Is your architecture designed with Anycast in mind, with health-driven BGP announcements and solid redundancy inside of each POP? And consider how Anycast will fail over, including between POPs. The third is operating. Do you have distributed observability, DDoS and incident runbooks, and strong change control around routing and capacity in place? Do you have trusted partners and vendors to engage with? The list is not complete, but if you work through these items with your teams, you will avoid many of the painful failures that we discussed. And that's it. I'm glad I trimmed this down on Brandon's advice from the 190 or so technical slides that I had originally. I hope that this session gave you a clearer picture of what it takes to deploy and operate Anycast successfully. I'll open it up to some questions. All right, let's see. We've got a question. You've spoken about Anycast from the network perspective. What about the actual infrastructure that serves the request? That's a great question. So in our world, Anycast and the network is the beginning. In fact, in our company name, we're NetActuate. An actuator moves things. And so we always start with the network. The network, to be useful, obviously has to connect to infrastructure. So in our world, that can be anything from bare metal servers, it can be co-located equipment, it can be our cloud platform using virtual machines, it can be Kubernetes clusters, and really the powerful thing about Anycast is that it can be a mixture of all of those things. It can even, if you're building your own global load balancer, span multiple providers and let you tune those things based on business needs or technical needs. So there's really no limit when it comes to the kind of infrastructure that you can connect to. Let's see. All right. Oh, that's a good one. I'm using AWS today. is it possible to Anycast into my existing AWS deployment to improve performance? And how can I do that? It's actually more common than you think. We all understand the cost models involved with hyperscalers being charged for every bit and byte. I don't think a day goes by that I don't see a multi-million-dollar a month invoice where it seems like there's just insane margin stacking on whatever the infrastructure is in AWS. And so it's really common for large customers to start to look at the pieces that they can move out of AWS, but you might be using something like EKS or have specific services that have painted you into a corner. And so how can you do that? Does it still make sense, and is it cost effective? And the answer is yes. By building sort of an Anycast shield or an edge, you can start to move really costly services out of AWS. And then you can use direct connect ports, cloud on-ramps, IX peering, and different things for your control plane and to keep that core application data in AWS. So in some ways, you can really have your cake and eat it too. And it's always interesting to look at a project where someone is heavily invested and deployed into AWS or any other hyperscaler. Look at which pieces can be moved out and then start to do that in a really systematic way. And that can be very cost effective, especially with the multi-year intense pricing that we see across AWS. Let's see, it looks like we've got a couple other questions and then we'll wrap up. Oh, here's one about the Cloudflare AWS outages. So what type of network redundancy plans for AWS and Cloudflare users could have been applied to avoid the recent outages? Yeah, I think this really has to involve both the business in your company and the technical team, because it's got to be a strategic decision. If you're operating a global SaaS service and it's important for you to be online, how much control do you want? How much ability in terms of DR and your BCP strategy are you going to want to take the driver's seat or be in the driver's seat versus sort of blindly trusting these platforms? Because I think we've seen 3 major outages in the last 6 weeks now with wide-ranging impact. You can't just blindly trust them. And so, for companies that have built out their own Anycast edge, even if it's just DNS, they were able to avoid a lot of these issues. If they've moved services there, maybe they had some things still in AWS, but they were able to serve user requests instead of being down. I think it was ironic that the popular site downdetector.com went down due to one of these outages. So, really at what point does it make sense for you as a business to invest in being sort of the arbiter of your own destiny? And it's very possible to do that with a global Anycast deployment. And it's something that I strongly believe if you're providing services at scale and you're doing it globally, you should consider. All right. I think that's about it. So we're right at about 40 minutes, and I think we'll wrap this up. So I guess in closing, I'd love to hear what you're thinking about Anycasting. Are you planning global DNS, an API front end, or something more specialized? I tried hard and I succeeded, except for now, in not mentioning AI at the edge in this presentation, which is another topic, especially with inference and agentic AI and everything else. So if you'd like to reach me, you can do that by emailing mark@anycast.com. You can also find a lot more material on anycast.com regarding this topic. Thanks, and have a great day.